All right, to continue with the excellent base that we now have, I'd like to introduce our next speaker, equally as impressive. I'd like to introduce, it's my great pleasure and honor to introduce Rohi Hourvitz. He's an entrepreneur and a strong advocate of innovation in healthcare technology with a huge passion for leveraging technology to find solutions. Rohi found Fertile AI, believing that AI could significantly and positively impact reproductive medicine and thereby address a number of challenging that we face in this field today. So over the last 2.5 years, he's guided Fertile AI into developing AI algorithms that can enhance the success of fertility treatments by offering personalized recommendations for transfer timings, medications, and dosages. This is something that we really need in our field. His singular knowledge and expertise of AI as related to fertility treatments has led Rohi to be an invited speaker at professional conferences globally and reflected through his contribution as shared author of numerous publications, articles, and abstracts. Prior to founding Fertile AI, Rohi made significant contributions in the digital health sector, so he's not his first rodeo. He's deploying solutions that were in hospitals worldwide. So without further ado, I'd like to introduce Rohi. He's going to be speaking about the role of AI in reproduction from a clinician's perspective. Thank you so much, sir.
Thank you.
So this is just forward, backwards. I think we got a laser. Awesome.
I've never had so many words said about me before, so thank you. So I'm going to talk a lot more software, less robotics, and it's going to be challenging coming after such interesting videos and success. So I'll be talking about artificial intelligence from the clinical perspective, from the clinician perspective, a lot less from the lab. And just in terms of conflict of interest, I'm the founder and stakeholder at Fertile AI. So I'm not going to talk too much about what artificial intelligence is, as this has been covered significantly. But one thing I would say is that it's not magic. At the end of the day, artificial intelligence is statistics. We're looking at input and output, just as was done 10, 15, and 20 years ago with linear regression. So I'll start a bit with the disparity between AI in the lab and AI for clinicians. I went into PubMed and I checked for embryo selection, artificial intelligence. I found close to 283 publications. I didn't even look for oocyte and sperm, and there's probably a lot more that wasn't covered here. And I went in and did the same exercise for everything that isn't in the lab, and there's a lot of different things going on there. So for ovarian stimulation, I found 39 results. For intrauterine insemination, I found 4 results. A few of them were duplicates, and then for frozen embryo transfer, I found only 16 results. And what I want to do today is I want to cover some of these publications and go over how they can help us and how they can improve clinical outcomes and why I think more should be invested in these kind of publications. So let's start from the challenges of performing artificial intelligence on the clinical side. So one is data. It's a lot more difficult to find quality data when talking about clinical decisions, as we need to follow a lot of different things. We need to look at the dosage that was given, the different ultrasound results, the blood results, and finally the clinical outcomes. And it's a lot different than doing in the lab where you have an image and you know whether there was a pregnancy or not. There's a lot of, let's say, bad data in this space. And I think the hardest real thing here is what would have been. Let's talk about initial dosage as an example. We would know if we gave 250 FSH, how many oocytes were retrieved, but we will never know what would have happened for the same patient on the same cycle with 300 dosage or 350 or 400. And I think this is one of the hardest things that we need to tackle when we develop these algorithms for clinical decision making. The benefits, I think, are clear: increased clinical outcomes, reduced medication costs, which is a huge factor, and patient convenience. If we give less injections, it makes things a lot easier for the patient. And a lot of what I'm going to show you today is already in use, and so this has actually been used in clinical practice. I'm going to start from ovarian stimulation, go over to frozen embryo transfer, and if I have time, touch a bit on intrauterine insemination, although I'm not sure I'll be able to get there as this is only 20 minutes long. So for ovarian stimulation, we've had a lot of different artificial intelligence approaches. The first one was done by Lettery, which tried to actually mimic managing an ovarian stimulation cycle from start to end with multiple decision points. Since then, we've had a pregnancy outcome prediction. We've gone through initial stimulation dosage, trigger day selection, antagonist timing, all across the board. And I'll be touching on a few of those throughout the lecture. So first of all, we have initial dosage, which is one of the real first decisions a clinician has to make. And the advantages of selecting the optimal dosage would be the optimized oocyte yield, reduction in unnecessary medication and associated costs, and then finally reducing injections from patients, which is a big, big deal. So I'm going to go through a few articles, and I think the most interesting one was one that was done almost 15 years ago now, or 13 years ago, and that was initial stimulation dosage by Lamarca. And what he did is he created a nomogram with standard linear regression, which he would give it the AMH, AFC, and it would tell you what the stimulation dosage that you gave will give as an oocyte yield. And I think this is an interesting take on how so many years ago we already had these algorithms. This isn't something that's new. It's just that we can probably do it better due to more data today and better computing skills. We also had this was published last year, a linear regression model for detecting the optimal dosage, a KNN-based approach, which is an ability to detect based on certain parameters what are the closest patients to this specific patient and how they reacted to similar dosage. In this article, they showed that they can improve in a retrospective analysis the amount of mature oocytes by 1.5 just by selecting the optimal dose, and also reduce the amount of dosage given. And another linear regression, which was done in the East, which showed how to select initial dosage and also change dosage throughout the process using artificial intelligence. Next up, we have trigger day selection, which is also a major decision point you have to make. There's been multiple articles published here, and the advantages are very clear. I mean, we're talking about optimizing oocyte yield, reducing unnecessary medication, and another aspect of this is also balancing out the lab. If I can better select what the best day for a trigger is, and if there's more than one, I can then balance out the amount of retrievals done on the lab throughout the week and reduce those peak days that a lot of different labs have. I'm going to look at one article which I was involved in writing. We were looking at a total of 12,000 cycles from 50 different physicians, all done in the same lab. So by that, we managed to reduce the bias of the lab when we were looking at the data here. Out of those 10,200 cycles, we removed a few cycles due to not enough data, incomplete data, and we got to 9,600 antagonist cycles. We then split that into ICSI-only cycles in order to also measure the amount of M2 cycles. Each one of these were split into train data, which is what we use to actually create these models, a validation set and a test set. The test set is completely invisible to the model and then used to accurately estimate its value. So when we looked at one of these cycles, we needed to split it into different samples. So if we're looking at this specific case, we looked at this as a cycle which has trigger in 4 days. We then looked at these two tests together as trigger in 2 days, and then finally as trigger today. And by that, we managed to multiply each one of these cycles and give a different prediction based on when the retrieval would be. We took this over the 10,200 cycles, and we created tens of thousands of different cycles. In addition, we added other demographic information, height, weight, and other parameters that were available to us. And then we created models that predict how many mature in oocytes, how many mature and total oocytes you would have based on the day of the prediction. So if you would do trigger today, this is the amount of oocytes you would have. If you do trigger tomorrow, this would be, and then finally in 2 days. And we got a pretty nice correlation, pretty good correlation of R-square of 0.73 on our second model, 0.71 and 0.66 on today, tomorrow, and in 2 days, with a min average error from 213 to 247, which is pretty good, specifically because we had a lot of high amount of mature oocytes. So just as an example of how this would look, when we're looking on a cycle that was on day 8, stimulation day 6, let's see if this laser works. The machine can tell you, look, this is too early to trigger. This would not give you optimal oocytes, so bring her in for a test in 2 days. So this is a real case. She came in again. Oh, she came in again in 2 days. She came in again in 2 days, and again the machine said, look, you could trigger, but this is not optimal, this is not optimal, coming in again in 2 days. And finally, when we got to the point where trigger is available, it tells you this is optimal, but this is less optimal. So now the doctor can decide, should I trigger today or tomorrow based on whatever parameters he wants. In this specific case, the machine thought there would be 16 oocytes, and that's what it actually has. Obviously, I picked the best example. And then, you know, I've showed this slide before, and a lot of physicians come up and say, why do I care? So why do I care if I can predict? And so we wanted to do a retrospective analysis comparing what we call matched and unmatched cycles, where we thought the doctor did properly compared to where he did non-optimally. And the way we did this is we looked at a specific cycle, we looked at the predictions today, tomorrow, or in 2 days, and we did an analysis on where the improvement would be. In cases of improvement with over 10% increase, we recommended the trigger days. So 2 days with less than 10% would be equal. And then we did a retrospective analysis on what we call matched and unmatched groups.